Okay, so binary will have 0 or 2 childs at most. So that means if I have a root node like this, so it can have 0 or 2 childs. So let's say it is having only 2 childs. So again, this will have 0 or 2 childs. So this is a binary tree. Okay, this is a perfectly fine binary tree. This is binary tree. So how do we create a binary tree? Basically, this is nothing but a node which is having a data part and left and right pointer. Why I'm doing using left and right? Because we are damn sure that there will be only 2 pointers. There will be only 2 child. That's why I'm naming those two pointers as left and right. So if you want to implement it in this fashion, the one that we have seen in this way, so it can also be done in that way. So it will be node data, and then you will have an array of child, some let's say like child array, which is having a size of 2. So this 2, as is it's fixed, so for our convenience we are splitting separately in individual variables. Okay, so this is about binary tree, and most of the programming questions or let's say competitive questions will be on binary tree only. They will not ask you an array tree. In a very rare scenario they will ask an array tree, because first of all, tree's implementation is a little difficult. Statement is both of them is fine. It is just a collection of child and parent. So if you just know how to traverse or how to perform logic in binary tree, it is automatically known that you also can handle an tree. That's why it is always a binary tree that is given to you. Okay, now let's see what are the different variations of binary tree that we have. So this is done. So again, so the time complexity of us to reach this one particular node depends on the height of the data structure. So it is order of h. So our entire intention or the main reason to consider nonlinear should be to make this h as less as possible, as less as possible. Okay, so if this h becomes equal to n, then the entire reason of creating nonlinear structure is now gone into waste. So this will not be the case. So we want to avoid this condition, and we want to make this height as less as possible. Even in this case, in the NRA tree, if I want to go to this node, it is all depending on the height. Okay, so that is one thing. We will see like how we can reduce the height and all the stuff. Okay, so let's talk more about binary trees now. So what are the different types of binary trees? Any questions till now, guys?
No, sir.
Okay. So let me write different types of binary tree. So first one will be the normal or full, or basically full binary tree. Then there is complete binary tree. Then there is degenerated or skewed. I don't know the spelling is KYWED, something like that, skewed. And then perfect, and then balanced. Okay, so full binary tree is a tree where all nodes have either 0 or 2 nodes, 2 children, either 0 or 2 children. Okay, that is the definition. So any tree which is having either 0 or 2 children as a node, then it is known as full binary tree. The complete binary tree is important. So out of these three, this is very important and this is very important. So important as in the problem solving sense and all the sum, we can expect these two things. To implement efficient algorithm also, we can expect these complete and binary. Okay, what is complete? So complete means all the levels are completely filled. All the levels are completely filled. Last one should be from left to right. Last should be from left to right. Okay, that means what is the level basically? So if this is a tree given to me, this is level 1, this is level 2, this is level 3. Okay, depending on how many nodes I have, I will have levels of the tree. So this is level 3, this is level 4, this is level 5. So complete binary tree is a tree where all the levels are completely filled. Okay, this one is filled, this one is filled, this one is filled. But level 4 is not filled, but I am still going into level 5. So this is not a complete binary tree. So in order to reach level 5, I should have come a level 4 as complete. So it should be something like this. Okay, it should be complete thing. Okay, so this is level 4. And also, let's say I have level 2, level 1, level 2. So now when I'm creating level 3, it should be from left to right. It's not that it should be from right to left. We cannot have like this. This is not a complete binary tree. So this last level should also be filled from left to right. So this can be considered a binary tree. Sorry, complete binary tree. This is fine. And then this is also fine. This is also fine. So if you see, these are completely filled from left to right. So that is the definition of complete binary tree. Degenerate binary tree is a binary tree where it grows only in one direction, one particular direction. So kind of a linked list. It grows like a linked list. So example of this would be, let's say this node. Let's say this node, this is having a right child, and this is having again only left child. This is having right, this is having right, and this is having right. So this, if you see, it is not at all maintaining our tree properties. So if you want to traverse this thing, it is kind of a linear way. We have to go through all the elements. So this type of tree is known as degenerated trees, and again there are two types of it. They are left skewed or right skewed tree. If the tree is only growing on the left side, then we call it left skewed tree. If the tree is only growing on the right side, it is known as right skewed tree. Okay, so this is one thing. So every node only one child. Okay, so now perfect. So perfect is one another binary tree where all internal nodes have two children, have two child, and all the leaf nodes are of same level, and all leaf nodes are at same level. Okay, so this is a definition. So now you might have a confusion between this and these two. So remember, so first thing first, a full can have 0 or 2 child. Okay, that is one thing. But my perfect will always have all the internal nodes will have only 2 child. That means what? Let's say, let me clear it. So what is internal basically? So any node apart from leaf nodes are considered as internal nodes. Okay, so that is one thing, internal nodes. And the second condition is that all the leaf nodes are of same level. That means what if, let's say I have, these are my leaf nodes, let's say, so all the parents, so their parents should have both should have two children. Okay, so like this. So this is a complete full or say perfect, sorry, perfect binary tree. So perfect binary tree is a binary tree which is filled at all levels. Okay, consider this is a perfect binary tree. And if you are extending, so if you're creating one more thing, so let's say this thing, this is not a perfect binary tree because all the leaf nodes are not at same level. So if you see, this is a leaf node, this is a leaf node. So we have to make all the leaf nodes the same level. So this could be one, this could be one, this could be one, and this could be one. So in this case, now all the leaf nodes are at same level. Okay, but the previous condition, all the internal nodes should have two childs. Does it follow that for condition? No. This is the internal node which is having only two childs. So this is not the one. So we have to fill this thing. So now this is a perfect binary tree. Okay. So all the leaf nodes are at same level and all the internal nodes are having two children. Okay, so in contrast to full is nothing but which will have only 2 or 0 child. So it could be like something like this. So, this is a so this can be considered as full because it has either 0 or child, 0 or 2 childs. So it is having 0 childs. It is having 0 child. It is having 2 child. It is having 0 child. It is having 2 child. So come, this is fine. This is known as full binary tree. Whereas complete means what? Complete means all the levels are completely filled. So only the last level will be missing. So if I just copy paste this thing. So if I just remove this thing, okay, so this can be considered as a complete because all the levels are completely filled and the last level is completely filled from left to right. Okay, so this is considered as a complete binary tree. So it can also have one child. So it doesn't have restriction on number of child. So a node can have 0 child, 1 child, or 2 child. Doesn't matter. The only thing that matters is all the nodes are completely filled. All the levels are completely filled. Okay. So this is all about this thing. Okay, last one we are left, it is balanced. Balanced binary tree is a tree where height is maintained and height is always log of n. Okay, that means height is always minimum. For any given tree, log n is the minimum height. So for any tree, if you are maintaining the height as log n, that means the tree is known as height balanced tree. Okay, so how do you maintain log n and all we will discuss, but this thing you just remember that any tree which is having a height as log n is considered as a balanced tree. Okay, so these are the different types of tree. Take a note of this thing and let me know in chat when you are done. Let me know in chat, guys, once you're done with this notes. Come on, guys. Are you guys done taking the notes? Let me know in chat. Only one person has replied. There are 150 members in this session. Okay. Okay, let's now move to the next part, and which is very important. These are like properties of a tree. Okay, properties of a tree. So there are two things that you should remember here. One is height of a tree. The two things that we will discuss here. Okay, first thing that you should know is height, which we represented with H, and level, which we represented with L. Okay, L. So H starts from 0, greater than or equal to 0. Level starts from 1. Okay, so what is height? So let me draw something here. So again, height definition is actually depended on the program statement that is given to you, problem statement that is given to you. So for our example, we will consider height starts from 0. So I will explain you what it is. Let's say this is a tree. Okay, so this is nothing but height 0. Okay, this is known as height 0, means this level. This is known as height 1. This is known as height 2. This is known as height 3. This is known as height 4. So basically now we are considering a number of edge as the height, or which represents the this thing. Okay, so this is height. Few examples, if you only a root node, it is height 0. Yeah. So few of the online exams or online things will have a concept of depth. Okay, that concept can look very similar to height, but you have to make very sure. So depth sometimes they calculate as as a number of edge between the nodes. Sometimes it is calculated as number of nodes. Okay, so if I'm calculating the depth of this thing, so it will be like, if I'm calculating nodes, it will be 3. If I'm calculating edges, it will be only 2. So be very careful when you're dealing with depths. Okay. So the depth concept will be given in the question itself, that we are considering the number of edges as a depth or number of nodes as a depth. Okay. That is completely different topic. But for now, we are considering height. Heights are nothing but height 0, height 1, height 2, height 3, and height 4. Okay. That is one thing. And similarly, there are levels. So we call it as level 1, level 1, level 2, level 3, level 4, then level 5. Okay, so this is the base criteria, base knowledge for the properties. So now let me write those properties. Okay, so what are those properties? So the first property is okay, so the first one is number of nodes based on height. Okay, so if the height is given, how can I find the number of nodes? So if h is given, how can I find number of nodes? Let's say n is the number of nodes. Okay, so the minimum number of nodes for this thing would be, minimum number of nodes is nothing but h plus 1. Okay, so if height is 0, minimum number is h plus 1. If height is 1, so consider this thing. I don't know if I can go. Okay, I will explain you. First, let me write it here. And the maximum number is nothing but, maximum number of nodes is nothing but 2 power uh, 2 power of h plus 1 minus 1. Okay, so this is the maximum number of nodes that I can have according to the height. So the second property is height based on nodes. Okay, if n is given, how can I find height? So here the minimum height would be for any binary tree, the minimum height is log n, and the maximum height will be n plus 1, sorry, n minus 1. Okay, so these are the third property. The second property, the third property is node based on level. Okay, so if L is given, that means level is given. How to find number of nodes? So first thing first, minimum number of nodes, maximum number of nodes. Okay, max number of nodes is how much? L power the level, sorry, 2 power of L minus, this is a maximum, and minimum could be 1 because a level can have only one node is equal to 1. Okay, so these are the three important properties. I request you to take a note. I'll give you time to take notes, but first let's explain or understand this. Okay, so the first thing first, what is, if height is given, how many nodes I can find? So I am talking about the entire tree. So these first two properties are all about entire tree, whereas this property is only about a level. Okay, so if minimum nodes of the tree, so a height is given as 0. So what is the minimum number of nodes? It could have h plus 1. That means height is 0 means what? It will have at least one node. Okay, this thing. If height is 1 means what? It will at least have two nodes. So h plus 1. So height plus 1 will give us a total number of nodes, total minimum number of nodes in the tree. Okay, similar to this thing, there is a maximum number count. So if my height is something like, let's say this is my complete tree. So, okay, I cannot have more than these many number of nodes. So in here, if you see 0, 1, 2, so the formula will be 2 power of 2 plus 1 minus 1. So 2 power of 3 minus 1, that is 8 minus 1, 7. Let's consider this. So it is 4, then 3. Yeah, it is 7. So that is how we do it. So maximum number of nodes is nothing but this formula, depending on the height. Okay, so now let's consider number of nodes is given to you. Let's say n number of nodes is given to you. Now we want to find out height. So for any given tree, the height of the tree is minimum when it is balanced. That means every node can have at least it is splitted properly. So something like this. Okay. So in this case, the height will be how much? Let's say I have explained you this thing in binary search basically. So here it is 2 power of 0, 2 power 1, 2 power 2, 2 power 3. Okay. So this 2 power 3 is nothing but this entire sum is nothing but n. So the last one will be 2 power of k will be equal to the n. That means all my nodes will be exhausting. So a k is nothing but the height. If you see 0 is the height of this thing, 0, 1 is the height of this thing, 2 is the height of this particular node, 3 is the height of this. When I say height, I'm consider if my tree is ending, then this is the height. If my tree is ending here, this is the height. Okay. So here for the 2 power kth level, k will be the height. So how do I find k? I just pass 2 here, so it will be log base 2. So for any complete binary tree or a balanced binary tree, the height is log of n. So, and that is only the minimum height. So if the tree is properly formed, okay, something like this, then it is order of log n. So if the tree is something like this, okay. So in here, the height is now n. Okay, so it will be only n. So that's why the maximum height is nothing but n minus 1. So as we start from 0, and there are n, so there are n elements as we start from 0. So it is n minus 1. Okay, so that's why it is maximum height is n minus 1. So clear with these two properties. So the third one would be the nodes based on level. That means how many nodes are there in a particular level. So let's say if I take this particular tree, so here it is level 1, level 2, level 3, level 4. So any particular level can have only one child, correct? So this is also one level. So it is 1, 2, 3, 4. So the minimum number of nodes is only 1. See this. but the maximum is 2 power of L minus 1. So let's say this one, 2 power of 1 minus 1, that is 0, 2 power 0 is 1. That's why it is having only 1. So now the second level is 2 power of 2 minus 1, that is what, 2 power 1, that is 2. That means this second level can have two childs. And then so on, that it will become 2 power 3, 4, 5, 6, 7, 8, 9, 10. Okay, similar to this thing. See this. Level starts from 1, so it is 1 minus 1, that is 0, 2 minus 1, it is 1, 3 minus 1, it is 2, and so on. So these are the formulas, okay? So maximum number of nodes is 2 power of L minus 1, minimum number of nodes is this thing. So these are very important for formulas. So basically for time complexity, if you are analyzing and all, this is how you can easily formulate your complexities. Okay, and these are the definitions of the level. So this is height. Height starts from 0, level starts from 1. And when we are saying height, we will say the height of entire tree. So I just written here 3 because let's say 3 is ending here, that means it is the height. Okay, whereas level are for one particular levels. Okay, so if you see these are trees, these are only level. Let me clear this thing and you take a note of this entire thing. Okay, take a note of these properties, guys. These are important properties. So if you have any questions, let me know. Take a note of this thing and then we'll resume. Remember one thing, height is different from depth. Depth will have a complete different definition according to the program problem statement. So sometimes depth might be represented as a number of edges between root node and the leaf node. Sometimes it might represent as number of nodes between leaf node and the root node. So it will be clearly given to you in the problem statement itself. Take a note of these things and let me know once it is done. Let me know in the chat. Okay, so let's move ahead. Okay, so the next thing that we will see here is, let's see, the trees we have discussed, n-array trees we have discussed, binary tree also we have discussed, properties of binary tree, different types of trees we have completed. Let's talk about BST. Okay, so BST is a specific, again, subdomain of a tree. So under trees we had, so if this is tree, the subdomain basically an array tree, an array. So under this there was a subdomain known as binary tree, binary, binary tree. So under this we will have one more subdomain known as BST. Okay, BST. So this BST is nothing but a binary tree first of all, but with some restrictions. So the insertion and the deletion order, so not insertion deletion, the order of the elements are different. So the property that it should follow, so for it should follow the properties of binary tree first of all. Okay, so first now what is a binary tree? So it should have 0 or 2 children, that is one thing. And all the different types of tree that we have seen, completed, full, complete, full, perfect, all those tree are still valid in BST. But only one condition that is added here is the root level, the root node or the root value, root should always be less than uh, the child, left child. The root should always be left should always be less than root, and root should always be less than right. Okay, that is the rule that we have to maintain, that the root should always be left should always be less than root, and root should always be less than right. Okay, so if I have a tree like this 4, so that means my left subtree, the entire subtree should have a values less than or equal to 4, whereas my entire right subtree should have values greater than 4. Okay, that is one thing that you have to follow. So depending on this particular order, we have to insert, and BST can have doesn't generally have duplicate values, but even if it is having duplicate, just make sure that you follow this particular rule. It should be less than or equal to, right than or equal to. Okay, so let's say 4. So here I will insert 3. Let's say how do, okay, so let's talk about insertion and deletion. Insertion, deletion. We will talk about insertion, we'll see the code, then we'll come back and talk about deletion. Okay. So let's say I'm inserting 4, 5, 1, 3, 9, 8, 7. Okay, these are my nodes. So first thing first, 4 will be inserted. Okay, this will be by root, and then 5. Now, this being 4 is nothing but what? Less than 5. So I am very sure that my 5 should be inserted on the right side. So here I'll insert 5. Similarly, 1 is less than 4, that's why it is inserted here. Now 3. 3 is less than 4, so it should go here. But 3 is more than 1, so it should go here. 3. Okay, 9. 9 is more than 4, it should go here. 9 is more than 5, it should go here. So that's why it is here. Okay, then 8. Again, 8 is more than 4, 8 is more than 5. 8 is more than 5, but 8 is less than 9, so it should go here. Remember, we cannot add it like this. Okay, we cannot do it here because my left node should always be less than right. That means what? My all the nodes here should be less than 5. Okay, that is one thing. Less than 5, but again more than 4. All those at every node, at every level, that at every node we have to maintain this particular rule. Okay, then what are we left with? 7. So it will be how much? So it is more than 4, it is more than 5, it is more than 9, it is more than 8, sorry, less than 8, so it will be 7 here. Okay, this is how the tree will be. So if you see, every node is having either 0 or 2 childs, so it is a binary tree. And yeah, that's it. So this is a binary tree plus with this rule. So it doesn't follow particular order like perfect, full, or complete. No, it doesn't guarantee. So that's why BST is good in terms of searching. So if you see, searching is very easy here. So in normal terms or in any data structure, if you want to search, we have to do order of n traversal. So because we have to search a one particular data from the entire data set, we have to traverse the entire data set. But as the data set is maintained in this order, we are very sure that we can just avoid searching in the left side or right side depending on the value. So here my search algorithm will be order of h, where h is the height of the tree. So as just now we have seen in the previous slides that previous discussion, a height can be a minimum of log n. So this could be a minimum case, minimum. Okay, at the same time height can be n, n minus 1, that is maximum. So if you see, my odd time complexity of searching could be order of log n or order of n, depending on the tree implementation. So if the tree implementation is height balanced, then means it is order of log n, which is the minimum thing. So that's why we will see BST is helpful. No doubt it is very useful in help searching and all. Okay, but it is not balanced. Okay, that's why we will see alteration of BST, that is known as AVL tree. That is a balanced binary search tree. We will see, so that we maintain order of log n. But for now, we will not discuss AVL tree. So we will just assume that it is either log n or order of n, depending on our luck, like how is the tree created. Okay, and again, BST is dependent on how the tree is getting created. So if the insertion order changes, the entire tree structure will change. Okay, clear everyone with this BST, this rule and insertion order? Okay, so we will quickly see the that thing means implementation part, and then we will continue. So BST is very helpful in searching. That is first point that you should know. The searching time complexity is order of log n. Okay. This is very better when compared to the search time complexities in arrays and linked lists, that is n. Okay. And no matter arrays, linked lists, even in graph, if you are searching, the time complexity will be order of n, because in searching we don't know where the element will be. So you have to traverse all the elements. But as the BST is maintaining this particular order, we are very sure that we can skip few of the elements. So whenever we are skipping, our time complexity decreases. And if we are maintaining a one particular tree with a balanced height, our time complexity will be order of log n. Okay. So BST, if someone is asking what is the use case, it is very efficient in searching. Let's see the implementation of a tree. Okay, first thing first, I need a node class. Let me import. So first I need a class, as I said. So class will have three things. First thing is data. Then the next two things are the pointers, left and right pointer. I will just create a constructor. Okay, so this is created. So my node is done. So I will create one more class known as bstutil something. So it will have a logic of insertion. So insertion means what? How did we do insertion in trees? We have taken the how did we do insertion in linked list? We take the head, we take the data, and we return the updated head. Correct. So we will do it in same way. So we will write a no insert function which takes the root of the head, root of the tree, which takes the data to be inserted, and then it returns a new node, or it returns the new root. Okay. Okay. So now first things first, if my root is equal to null, that means what? There is no particular element to be searched or compared. So in this case, I will write return new node. Okay. So now there is one particular node which is present. Now I have to decide whether I have to go to the left side or right side. Okay, because I cannot so if you notice, every time I insert a element, it will be in the leaf part only. Okay, so if I insert something, it will not replace some value here, it will not replace let's say 6, it will not do it like this. So it will get itself inserted at the leaf part. So if I am at some element, that means there is some node, I have to decide whether I have to go to the left side or right side, because leaf node will be either in the left side or right side. So how do I decide is depending on the this uh, rule. Okay, whether it is left less than the data or the right greater than the data. So first thing that I have to check, if my root dot data is greater than data, that means the data that I'm inserting, or basically like this. If the data is less than root dot data, that means the data that I'm trying to insert is less than the root. So with the definition, all the element which is less than root should go to the left side, correct? So I will say that you recursively go to the left side and insert it. Okay, so I will give him the left pointer. So now it will start inserting from the left pointer. Else, you should insert into the right side. So once done, you return the root. Okay, so this is the insertion logic. So this will recursively go and insert into the tree. So let's see how it happens. Let's say this is my input. So 5, 3, 7, 4, 1, 6, 9. Let's say. Okay, so 5. So root is nothing. So it will just insert it here. So 5 is inserted and this is the root. Okay, now I'm inserting 3. So I start with this thing. So 5 compared to 3. So 3 is less than 5. So I say that, okay, you go and insert into the left side. But if you notice here, I'm also updating the left pointer. That means no, whatever he's sending me, this recursive function is sending me, that should be the left pointer. So now I'm going to this left side, which is null. So he checks that it is null. Okay, so it is null, then it will return the new node. So that means what, it will create some 3. Okay, and it will return this pointer. So whenever he's returning this pointer, this becomes a left. Okay, based on this line. So this is now pointing like this. So 3 is pointed here, and then again it will go back. Okay, 7. So same again, 7 will be pointed here. Then 4. So 4 will be added here. Then 1 will be added here. Then 6, it will be added here, and then 9, it will be added here. Okay. So yeah, so this is how my tree is done, created. Any questions in this recursive logic? This is a very simple insertion logic, guys. Okay, now let's see how do we traverse the linked list tree. Okay, so traversal. Traversal. Non-linear DS. For any non-linear data structure, there are basically two types of traversal. So linear data structures is having only one type of traversal, that is linear traversal. So we cannot do any other traversal techniques because the data is stored in linear fashion. But as the non-linear data structure, we have to take a choice. Okay, so with this choice, we come up to these two types of traversal. One is DFS, depth first traversal. Something like this. S means depth first search. Basically, the full form of S is depth first search. Depth first search. And then there is another called as BFS. So BFS means breadth first search. Breadth first search. So FS we are writing because it is a terminology. So I will just say DFS and BFS. So remember, it is depth first traversal or depth wise traversal or breadth wise traversal. Okay. So what do you mean by depth wise traversal? Depth wise traversal means when I start a node, and now I have to take a choice. So I have to go to the left side or I have to go to the right side. The same happens in graph also. In graph, there are multiple nodes, so we have to take I have to take a decision on which connection I have to go. Okay, so same here. So now I have to decide which side I have to go. So if I take as a DFS and if I take a left side, so I will complete the entire left part till I reach the null value. Okay, that means what, I am going at the entire depth. Okay, this is depth wise. Okay, so 5 from 3, then 3 to 1. Okay, so depth is completed. Then I'll go back and again I'll complete whatever my remaining depth is left. Okay, so this is known as depth wise search. Whereas breadth-wise search means I will not go depth-wise, I will just go level-wise. So if you see 5, first I will go to this level. So this is my breadth. Okay, this is my breadth. Then the second thing, this will be this. So then it will be something like this. So this is how my BFS work in tree. Okay, level-wise. So in trees, if I have to give specifically, trees, trees is having DFS and trees is having BFS. So DFS is of 3 types: in order, a pre-order, post-order. There is a slight difference between these three I will explain, and this is known as level order. So these are the traversal techniques in tree. So let's consider a graph. Let's say a graph is something like this. Okay, so if it is like, if I'm here, so DFS means what I will do. Let's say I have to decide now. I have to decide which route I have to go, which path I have to go. If I take this decision as this thing, so I'll completely traverse this path. Then I'll come back. Then I'll completely traverse this path, and I'll come back. Completely traverse this path, then I'll come back. Completely traverse this path, then I'll come back. Okay, then again I will like, oh my. So then I'll go to this path, and then I'll come back. So similarly here, something like this. Okay, this is how my depth first traversal will be. But whereas my BFS means what, I will go breadth wise. So I'll first go to the immediate connections. So these are my immediate connections. Okay, then I'll go to the next level of connection. So what are the next level of connection? These are my next level of connections. Okay, then I'll go to the another next level of connection. So this is it. Okay, so this is how breadth-wise traversal. So it will grow like this. Breadth-wise will grow like this. So like something like this. So it is expanding in all the directions. Whereas depth-wise, it will first go to the end, one end, and then it will come back. Then again, it will go to the end. Okay, so this is one thing. So now coming back to trees, so DFS can be implemented in 3 ways: in order, pre-order, and post-order. BFS can be implemented in only one way, that is level order. So in order means what? First, we will, whenever we are going depth-wise, so that means what? So as we are going, so depth-wise or breadth-wise, we are talking or discussing about the direction or the flow that we are going in. But how do we perform the operations? So in here, in order traversal, what we will do is first we will go to the left side. Okay, then we come back and then we perform the logic. Okay, so basically it will be something like this. So first go to the left side, then perform the logic on route. Okay, whatever logic you're trying to do. So if you're just printing, then you just print the logic. If you're just doing finding something, then just do it. Okay, then we again continue to the right side. So this is nothing but left, root, right. Okay, this is nothing but in order. Pre-order means what? First we will execute the logic on route. Okay, then we will go left, then we will go right. Okay, post order means again we will first go left, then we'll go right, then we'll go route. Okay, logic on route. Okay, so this is how the traversals are in nonlinear data structure. So one thing to remember, DFS and BFS, these are the different categories of traversal. So for trees, DFS and BFS are implemented in these 4 orders, these 4 ways. So in order, pre-order, post-order, and level order. One more important point to note here is whenever we are doing DFS, we should use the data structure stack. So to implement this, we have to use stack data structure. To implement this, we have to use queue data structure. Okay, so these are the 2 data structures that will help us in implementing these 2 traversal approaches. Okay, let's now see the in order traversal. Public void in order. So for now, I will just the logic of in order. I'm just saying that I will print the node value. So node root. So first thing first, if my root is equal to null, return. Okay, no need to do anything. Then what? This is in order. That means I have to go left side first of all. In order root dot left. Then I have to do the logic. So my logic is just to printing, just to print the value. System dot out dot println root dot data. Okay, then I will go right side. So this is my in-order traversal. So now you might ask, you said that we have to use trees, but sorry, we have to use stack, but we are not using stack anyway. Remember one thing, this is a recursive algorithm. So recursive algorithm, we internally use stacks. So we need not to explicitly define a stack to use it. If you are doing in an iterative approach, then we have to use a stack. Okay. So let's say we implement that one also, public void in order iterative root. So first thing, if my root is equal to null, return, else not I have to create a stack. So stack of node. So we have seen the I'm using Java's inbuilt stack. Okay, so stack dot push my root while stack is not empty. I will pop all the elements and push all the childrens of them. So a node is equal to stack dot pop. So this is now I am popping the values. So now depending on how you want to, if I want to do in order, then I will write the insertion order first. Okay, so the insertion order will be how is it? So first of all, I will push my elements. So stack dot push node dot left. Also, before pushing, I'll just check whether it is null or not. So this will avoid this corner case. If my node dot left is not equal to null, okay, then only push it. So this is how you have to do DFS in iterative way. Then I'm printing out the value. Okay, so this is the logic. Okay, so now let's first of all let's do some input taking. So scanner system.in. So int n is equal to int I is equal to 0, I less than n, I plus plus, root is equal to bst. Okay, let me make them a static so that I can directly use them. Bst util dot insert, take my root, take my data. Okay, so this will create the tree. So now I am just saying that bst util dot in order, take my root. So this will print the in order. So system. Okay, let us give some input. So 537 4169. 537 4169. How many are there? 1 2 3 4 6 7. See, so this is the in order traversal. So in order traversal, let's see what is the output and how is the output. If you see, this is a tree created. So I'll start from 5. I'll go to the left. I'll go to the left. I'll go to the leftmost thing. So nothing is possible. Then I'll print. So 1 is printed. Then I'll go to the right. Nothing is printed. Then I'll go to its parent. So 3. Then I'll go to its right. So even here, I will not print. First, I'll go to the left. So nothing is there. Then I'll print 4. Okay. Then to the right, nothing is there. So again, go back. So now I will print 5. Okay. So then I will go inside this thing. So first I'll go here, then I'll go here, then I'll go here. So nothing is there. 6, then I come back. Then I'll try to go to the right, nothing is there, and then I'll go up. So 7 is printed and then 9 is printed. So if you see in order, one more important point, if you notice, this is in sorted thing. So sorted. So in order of BST will always be in sorted order, will always be sorted, sorted, sorted order. Okay, that is one part. Clear everyone with this in order traversal? So we have defined a in order traversal. Let's do this thing in order of iterative approach. This will not be in order, I think. VST util. It is 5 7. So first of all, it should be here. So it is not taking from the uh, last part. So we are just popping the value. So first 5 is inserted. So how it is implemented is, let's say, where is my tree? 5 3 7 1 4 6 9. Let me write here. So 5 3 7 1 4 6 9. So depth first search, what is happening is we are doing a pre-order traversal basically. So that's why it is 5 3 1 4 7 6 9. If you see 5, okay, 5 7 9. Okay, what am I doing here? Left and then right. Okay, 5 7 9. How is it 7 9? Okay, let's see. So first of all, we are inserting 5. Okay. So now when I'm popping 5, I am printing out the 5 value. Let's do it like this. Okay. Then I'm printing 5 value. Then I'm inserting 3. Then I'm inserting 7. Okay. So as I'm inserting in this way, my rightmost one is at the top. So then I'm popping out 7. So then I'm printing 7, and then I'm inserting 6 and 9. So 6 and 9 is inserted. Okay. Then I'm inserting, removing 9. So if you see, I'm going in this way. So rightmost, so it is nothing but root, right and left. So if I just reverse the order, it will become something like this. So 5 3 1 4 9 6. So now if you see 5 3 1 4, okay, then what? 7 6 9. So it is left right. So it is now maintaining left and right. So remember this is stack implementation. Whatever you insert at the last will be the one that is taken out. Okay. So we have implemented a pre-order traversal. So root, left and right. Okay, how do I say pre-order? Because in iterative approach, this is how we are doing it. So first of all, we are printing this thing, and then we are inserting all the values. So yeah, that is about stack traversals. Nothing but this is not in order traversal, it's stack traversal. Let me write stack iterative. Okay, so if the question is about to use recursion, then you can simply do it this way. And there are two more things. Let me write that one also. In order, pre-order. So pre-order means the date logic will happen first. Okay, logic on the root will happen first, and then the left and right. Then post order means the logic on root will happen at the last. So logic on root will happen at the last. So if you see, this will be pre-order. See, this is a pre-order traversal. Okay. So this is all about traversal, guys. So in order, pre-order, post-order, and level order we have not seen. So we have only seen the DFS traversal today. So we have only seen in order, pre-order, and post-order. BFS we will see, but later in tomorrow's session, or if we have time today, we will see. But we want to cover a few problem statements. Okay. So any questions in this file, in this logics, or in these lines of code? So these are all DFS. 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 I will share the entire file at the end of the session so that everyone can has this entire thing. If you want, let me give you. The problem is this entire lines of code will not go in one message. That's the reason. Yeah. So stack till stack it is not going. I will share the file also, but we, for those who are in mobile, just take a note or take screenshot of this particular thing. Okay, so this I have just implemented the pre-order traversal using stacks. The in order and post order will be very similar. You have to do some tricks with this stack.pop. So I'm just directly inserting left and right into the stack. Okay, so I don't want this. So this will make my stack store all the childs. But in order wise, if I want to see, I don't want to store my left. Okay, I just want to go. Uh, uh, Means I just want to go left, left, left. Then once I'm done with all the left, then I want to store the right. So somehow you have to do some uh, store it somewhere in the stack or maintain two stacks or something like that, and you can do in order traversals. Okay, using stack. Okay, now let's move on to the next thing, the delete. Okay, where is it? So insertion is done. So okay, so time complexities of insertion. So time complexity of insertion depends on again height of the tree because I am only inserting at the leaf node. Okay. So the worst case is that I have to insert it here. Okay. Now these are the worst case. So again, this is nothing but order of h, where h is the height. So as a BST, my tree can have a maximum height of n. So the time complexity of insertion is n in BST. So if the height is log n, which will be in AVL tree that we will see in latest coming session, the insertion will be order of log n in AVL tree. AVL tree is also a BST only. Okay, so insertion time complexity is order of n because we are not sure that how my tree grows. So my tree can go in order of n fashion as well. So that's why time complexity is order of n. And again, searching is again dependent on height. So BST height can be order of n. That's why searching is also order of n. So the reason, if you the main thing, if you see, we implemented from linear we went to non-linear so that my searching and traversal is better. But here when I'm in BST, my searching, insertion, and all is order of n only. So it is still order of n. That means it is of making no use why to use BST over a nonlinear data such as list. Okay, so that's the reason why we create one more variation that is known as AVL tree. This is a part where the tree is balanced. Okay, and that's why it is making use of all the properties of tree. So if we are maintaining a tree something like this AVL tree, our time complexity will be log n in all the cases, and that is what we need. So that's why AVL tree is preferred, and mostly in whatever data structure that you want, you see where the tree is there, they will always try to make sure it is a height balanced tree, because if that height is not balanced, then there is no point of maintaining a tree. Okay, so it can grow like a linked list, which makes no sense. Okay, so that's why only height balanced trees are preferred, and AVL tree is one such height balanced tree. Okay, now let's see how do we do deletion. Uh, so let me pre-order, post order. Okay, so post order means 1, then 4, then 3, 6, 9, 7, 5. Okay, so how do we do deletion? Come on, guys, can anyone help me here? What was it? 5, 3. So how do we do deletion in a BST? Put the answer in chat. So 5, 7. So what is step 1? What is step 2? So what is the meaning of deletion? So deletion means what? We are deleting one particular node. Let's say I want to delete 7. Okay. So first of all, what do I have to do? First, I have to check whether 7 is there in the data structure or not. Correct. For checking, what is the meaning of checking? It is searching, right? So first I have to search whether 7 is there or not. So first of all, I have to search. So I will have search 7. Okay, so searching time complexity is again dependent on the height. So my tree can have a height of n. That's why it is order of n. Okay. Once now searching is done, so let's say I have found 7. Okay, I want to delete this 7. So now how do I do? So first thing first, I have to decide whether this is a okay. So here it is. Again, there are two categories. It is a leaf node or it is not a leaf node, non-leaf. Okay. So if it is a leaf node, let's say 9 is the leaf node. Okay. So I want to delete 9. I can simply just remove this and return null. Okay, but here I cannot do like this. So here I cannot just return something like I cannot just say that 6 return 6 or return 9. So it will not happen. So I have to maintain all the properties. So first thing first, I have to decide whether it is a leaf node or not a leaf or non-leaf node. So leaf or non-leaf. If it is a leaf, then it's a easy thing. So we will see, we will just return null. Okay, so if it is a non-leaf node, then what I have to do? So if this is the case, so should I make 6 as the root or should I make 9 as the root? Question. So this can also have one more, like it can have like 8. Okay, it can have 20. It can have like uh, 5 something. 5 is already there. Let's say this is the one. So I cannot just simply make 6 or 9 as a tree because that will not be a proper thing. I'll explain you with an example. This tree is not having some good example. Let's say 10. Okay, let's say 30. I want to relate 30. Then it is having like 60, 50, 45, then 50, 55. Okay, 90. Okay, something like this, and it is having, let's say, 10. 10 is already there, right? So 15, 25. Okay, let's say this is the tree and I want to delete 30. Okay, so from the previous thing what you said, that whether I can put 15 or 60 here. So if I put 15 here, all my nodes to the left side should be less than 15. Correct? So if I just keep 15 here, so if I just keep 15 here, so my tree will be something like this. 15, it is 25. So what will happen to this thing? So it will be 60 and also it is fine. Okay. So, but my 25, it is missing. See, all the left side nodes should be less than my 15. So this is not correct. So this should be gone. So I cannot place 15. Similarly, if I place 60 here, Okay, so if I place 60 here, so what is it? So 15 will be here, and then it will continue to have this node 25. So here it is 90. So what about 50? So where will this 50 go? So where should I keep this 50? So I cannot just place 50 to this side because it should be more than 50, correct? So I cannot place 15, I cannot place 60. Both of them are wrong. Okay, so both of them are not correct. So what should I have to do? So this is the node I have to delete. So I have left and right child. So there are two ways. So first way is get maximum. So there are two steps or two ways. Get max from left subtree. Second one, get minimum from right subtree. Okay, these are the two things. That means what I have to replace 30 with either maximum from the left subtree or minimum from the right subtree. Let's take what is the maximum here, 25. So if I just replace it with 25, then it is making good perfect sense because 25, all the elements here will be less than 25 and all the elements here will be right than 25. Okay, similarly, if I don't want to take 25, I have to take the minimum of this tree. So minimum of this tree is 40. So if I place 40, all the elements here will be less than 40 and all the elements here will be greater than 40. Okay, that's why we have to decide based on these two approaches. Get the maximum from left subtree or get the minimum from right subtree. And it is up to you which one you want to take. Okay, let's say I am picking the first one. Let's say I'm taking the second one. Get the minimum from the right subtree. Okay, so once I take the minimum, let's say 40, so I will do what? I will replace 40 here, and then I will say that, okay, from this tree, you delete 40. So one point to remember is that maximum and minimum will always be a leaf node. Okay, so when I delete, I make this as 40. There are two instances of 40 here. One is at this point and another is this point. So I can again recursively say that delete 40 from this particular tree. So it will come and it will find, okay, this is a leaf node. It will just return and it will delete and return null. Okay, so this is how you have to do it. So first thing first, if it is a non-leaf, get the minimum or maximum from right subtree. Two steps. Okay, minimum or maximum. Okay, and then delete the replace, basically replace, then delete minimum slash maximum, whatever you have decided. Okay, so these are the steps. Okay, clear everyone with this delete theory? So we cannot just replace it with 6 or 9. We have to take either the minimum from maximum from the left side or minimum from the right side. Okay, let's implement that logic. So I will write a recursive solution to get the minimum. Public int get minimum. Okay, and it takes a root. So this is a BST. Come on, guys. So in BST, where can I find the minimum? Which path should I take? Should I go to the left or should I go to the right? Tell me, if a BST is given to you, where can I expect the minimum element to be? Left side, correct? So every time I have to go only left side. So if my root is equal to null, okay. So if my root dot left is equal to null and root dot right is equal to null, return root dot data. Okay, this is the minimum value if it is a leaf node. Else, this is not the leaf node. Then what I have to do? I'll just simply say you go and find whatever is the left value. Return get minimum of. Okay, so first thing first, if it is root dot right, we are not concerned. Okay, if root dot left is null, that means I cannot go beyond left. Okay, there is no more left, then it is root of data. Else there is some left value, then you have to find go to the left. So this will recursively go to the left, and then it will return the last possible value. Okay, one thing to make sure that we are not passing null here. So if my root is null, then it will become false. So I'll just add one more check. If my root is equal to null, then return -1 just for our not breaking purpose. Okay. So first I'm checking if there is any left existing to do this node. If yes, that means my smallest element will be in the left part. So I am going into this thing. If not, so that means there is no left possible. That means this is a minimum value. Okay. So now let's write the delete logic. Okay, first thing first, as I said we have to first search. So depending on that, we have to do. So if my root is equal to null, so if my root dot data, if my data is less than root dot data, that means my element is not here. So I will say root dot left is equal to delete root comma data. Else if data is more than the root dot data, that means it's in the right side. Okay, root of right comma data. So yeah, so now this is the else part, means this is the part where matching, that means data found or something like that, data found. Okay, in this case what I have to do, first of all I have to check whether it is a leaf node or not. So if my root dot left is equal to null, that means what, there is only one part, so we can have three conditions here. Let's say x, which is a leaf node, something like, let's say 7, this is the only leaf node. 7 which is only pointing to 9, or 7 which is only pointing to 6, or 7 which is only pointing to 6 and 9. Okay, these are the four conditions. So if it is leaf node, then there is no problem. But there is, if it is having only one part, okay, so I can just simply delete it and return this thing. So that is what I'm checking. If root of left is null, that means if my left is null, so I'll just return root of right. Okay, else so now if my root of right is null, return root dot left. Okay, see, if right is null, I will just return them. So if both of them are null, so the first condition itself will take care. So if left is null, it will return null. So this will handle both the cases. Now this is the case. Okay, left is not null and right is not null. So in that case, what I have to do, I have to get the minimum, as I said, minimum from the right subtree. Get minimum. It should be a static thing. Get minimum of right subpart, root dot right. Okay, so this will get the minimum value. So now what I have to do, I have to replace. So where are my steps? So the searching is done. So now leaf node is also done, non-leaf node. So I'm going in this path. So from non-leaf, I'm taking the minimum from the right subtree, and then I have to do replace. So replace means what, data root dot data is equal to minimum. Okay, so now that means technically the value that I want to delete is now gone, and there are two instances of the minimum part. So what I have to do is delete the second or the last minimum thing. So I will just recursively say that root dot right is equal to delete root dot right comma minimum value. Okay, so it will recursively go and find the minimum value in the right subtree, which will obviously be a leaf, and then it will delete that leaf node. Okay, once it is all done, we will just return node. Clear everyone with this logic? So these first two steps are for searching. This is when the data is found. So I am doing getting the minimum value, and then I'm replacing the minimum value, and then I'm deleting the minimum value. So if I just delete it, something like this, bst sort delete, I want to delete what? How is my tree created? Okay, let's say I want to delete 7. Okay, after this thing to the pre in order. Method delete in class cannot be given types. Okay, I didn't pass root. Okay, see, 7 is gone and it is in sorted order. So I am printing in order. So 1, 3, 4, 5, 6, and 9. So it will be in a sorted order only. If you are still not sure, let's do a pre-order. So pre-order after deleting, so it will get the minimum. So minimum here is 9, so 9 will be here. So pre-order will be 5, 3, 1, 4, 9, and then 6. So it will be the order 5, 3, 1, 4, 9, 6. See this. Okay. So delete is working fine. Now this is a delete logic. Just go through it. So understand recursion. If you are confused how the recursive functions are getting called and how they are working, that's the reason why I was stressing on the point that you should be very good in recursion, because non-linear data structures, most of the logics are very easy to implement only when you know recursion. So if you don't know recursion, it will be very difficult for you to think and write an iterative approach. Okay, so that's why I was stressing on the point that practice recursion, think in recursive terms and all. Okay, with this we have completed our BST. In our insertion, deletion, and traversal is also done. So insertion, deletion, traversal. In traversal, we have seen BFS. DFS we have seen. BFS we will take it up later in the next session. But this entire thing is complete. Okay, and get minimum value from the tree is also complete. We have seen. Okay, so we have to go left side only. But what if the tree is not a BST? In that case, what? How do you find it? Let's do some problem solving questions now. So the first problem solving question is getting the minimum value from the tree. Come on, guys. Are you guys clear with this BST? I'm moving ahead. Can we move? So time complexity wise, insertion is order of n because BST doesn't guarantee that the height will be log n. So it will be order of height where height is maximum of order of n. So insertion is order of n, deletion is order of n, traversal is also order of sorry, not traversal, searching is also order of n. Okay, so BST, though it is a tree, it is not at all maintaining the properties of tree. That's why we will see what is a balanced BST. Balanced BST, insertion will be log n, deletion will be log n, traversal will be log n. Traversal or searching will be log n. Not traversal, searching will be log n. Traversal is anyhow order of n. Traversal means we are traversing through the entire data structure. Okay, so now let's move ahead. So the first question is getting minimum value from the tree. So you are given a tree. Remember, it is not a BS tree. If it is a BS tree, then go to the left side. So this is how the tree could be, something like 8, 9, like 1, 3, 4, 5, 7, 9, 0. Okay. So in this tree, you have to return the minimum element. How do you find the minimum element in this from this tree? How and what should be the logic? Tell me in the chat. Traversing left side till the leaf node. No, and that is the trick here. This is not a BST. So it is not guaranteed that the minimum will be on the left side. If you see, uh, this is a minimum actually. This is 0. This is 0. So this is a minimum in this entire tree, and this is not in the left side. So going only to the left side will not work. How do you frame a logic for this problem statement? Come on, guys, very simple. Think in terms of recursion. At every node, what you will do. Let's say I am here. Okay, let's say I'm at this point. So in 3, what should be the input to the recursion? What should be the output from the recursion? And all the stuff you have to think now. Start thinking in recursive terms. So which type of order? So first of all, it is getting the minimum value. That means what, it is kind of a searching problem. So for searching, we have to do traversal. So which order of traversal will you do? Will you do level order or will you do DFS? In DFS, which one will you prefer? In order, post order, pre order. Which one will you prefer? Okay, depending on them, frame your logic. So you have to do first traversal. In traversal also, you have to understand what are you giving to the recursion function and what are you expecting from that recursive function. So once you have got that expectation, frame the logic. Okay, so from 3, if I'm going to recursion 4 and 5, what am I expecting from 4 and 5 recursive functions? So what should they return? So think. Okay, come on, guys, at least one answer. And this could be one of the simplest question on the trees. Okay, so if you are trying to crack product companies, first of all, they will not even ask you this particular question because it is very simple, very easy. So think, because you have to, in future you have to solve difficult problems than this one. So these are the stepping stones. Okay, so now you will think in recursion. So in the next problem you will think how to optimize the recursion. Okay, and then you'll improve. So if you are just giving up here, then you can never improve. Keep trying, keep pushing your limit. So think what you will do at every node. Again, I am repeating, at every node, what is the thing that you should look for? What is the thing that you will call? So recursive function means what, at one particular node, I am calling another recursive function. So when that recursive function is done, what is that I am expecting from that node? Okay, expecting from that function. So once that output is here, then what for logic should I perform, and what is that I should return to the my parent function? So think in those recursive terms. Okay, let me explain you. So any tree question, you first divide your problem statement into one particular subproblem. Okay, only assume that this is a tree given to me. Okay, so in this is a tree, I am at this particular position. So 3. So in this case, what I should write, so how my logic should be. So I can say that when I'm at 3, I will find the minimum from the left subtree and I'll find the minimum from the right subtree. Okay, let's say these two are returning me 4 and 5. So I have minimum 1, minimum 2, and then this is a 3, which is actual value. So in out of these two, I have to return the minimum. So the question is to get the minimum value. and I have 3 values. That means what? Out of this 3 value, I have to return the minimum element. So I will then return the minimum element to this thing. And recursively, if I just follow this particular process, my entire tree will be traversed and I can find the minimum value. So how will this work means, let's say I have 8, I have 3, I have 9, I have 4, I have 5, then 1, then 7, then 9, then 0. 9 and then 0. Okay. So now when I say that I have to go to the child again, what kind of traversal you want to do? First of all, let's do a pre-order traverse, post-order traversal, because that is what is making sense. First, I'll find min 1, min 2, then I'll perform the logic. Logic of what? Finding minimum value. Finding minimum value. Okay, so if you see, this is my left, right, and then logic. So it is nothing but post-order traversal. So from 8, I will say that, okay, you find the minimum from the left subtree, you find the minimum from the right subtree, you found the minimum from this thing. So when I'm here, so I have to return something very huge number, like positive infinity. Okay, so I will return this thing. And then it will find the minimum from the right subtree. So if you see left, and then it will go to right. So it will return infinity. So now when I'm at 4, I have 3 numbers. I have 4, I have positive infinity, and then I have positive infinity. So which one is the minimum from these 3? 4, correct? So this will return 4. So now it will get 4 from this side. And then again, it will return get 5 from this side. So at that 3 level, I have 3 numbers, 3 node, I have 3 numbers. So 3, 4, and 5. So which one is smallest? 3. So this will get 3. Similarly, he will start from 9. For 9, it will just get 1, and it will get 9, it will get 0. So at this node, it will be 9, 7, 0. What is the minimum? 0. So 0 will be returned. So from at this particular position, okay, I have written 9 two times. Okay, fine. At this particular position, it is 9, 1, 0. What is the minimum? 0. So 0 will be returned. So when I am at 8, I am having 3 numbers, 3, 0, 8, which is the minimum? 0. So I will return 0. Okay, this is how the recursive logic should be framed. At every level or every node, what is that logic you are performing? Clear with this theory at least? So I also understand that this is the first time that you might be trying to solve a trees problem, and no one will become an expert in just a 2-hour session. That is also very realistic. But one thing that I want to stress here is the more you practice, the faster you become good. Okay. So if you just leave it on to something like, okay, I will see it on weekends, that will never happen. Okay. Can you use Inorder? See, Inorder is again depending on how we want to perform. So in order, what will happen is I am going left, then I have to perform logic, then I'm going right. Okay, but this is not the condition that I want. First, I want to get the minimum 1. Okay, then I want to find the minimum 2. Then then I have the actual number. So that is the root number. So once I am following this order, at that time only I'll have 3 numbers at a time. If I'm performing in order also, it is fine. I will find the minimum and then I'll return the minimum of this thing. So in order is also fine for this problem, but post order makes more sense because it is the logic will be more clear and readable. So first of all, I'm finding 2 minimum number, then I'm performing the logic. Okay, you can use in order, you can use pre-order also, and it doesn't matter. Till the time you are making sure that you are returning the minimum from each recursive function. So that recursive function should return the minimum. Okay, that is the main criteria. No matter you do pre-order, post-order, in order, inside. Okay, nothing matters until unless you return the minimum. Okay, let's see the logic quickly. So here there will be a question like public int get min. Get min will take the root. Okay, so the first thing first, if my root is null, Okay, that means what? It is a null node. So if you see here, as we are finding the minimum, right? So whenever I reach null, I'm sending positive infinity, because I know that whenever I compare something with the positive infinity will never be considered as minimum value. Okay, similar to the logics I explained in the beginning of this training session, right? Whenever you're finding the maximum element, initialize the default value as minimum, negative infinity. Whenever you're finding the minimum element, initialize the default value as maximum, and that means what? Positive infinity. That's why I will return something like very huge number, and that I can easily get it through integer dot max value. Okay, so now first thing I will find min1. I will say, okay, you find the minimum from the left subtree, root dot left. Then you find the min2. Min2 will be find the minimum from the right subtree. Okay. Once you have min1 and min2, you have to return the minimum of these two things. So I will just return, and I have data also. Let's say data is equal to, I'm just writing just to make sure that you all understand. So out of these three variables, I have to find the minimum. How do I do it? Okay. Math dot min of min1 comma min2. So this will return me the minimum of minimum 1 and minimum 2. And then I have to again find a minimum of these two value when compared to so this is one value versus data. So this will find, I'm writing a shortcut, guys. So you know, right, finding the minimum value of between three elements. You can make use of if conditions as well. Okay. So this will find the minimum of these three values, and then I will return this. Okay, let's test it out. So I will say system dot out dot println. See, minimum is 1. Okay. So let me insert few more values. Let's say 8. So now the minimum will be 0. Okay. So the same thing we are doing is as a general ideology or general logic. It is not a logic very specific to BST. So if it was to be BST logic, we can simply use another method. Control V. Okay, so I'm using get min, right? So I can also use this thing. So where is it? Get minimum. So if you see this, we are only going to the left side. So we are going left side because we know it is a BST. So for any BST, the smallest value will be on the leftmost part. So we can use this one also. BST util dot get min. Okay. So both of this will return the same answer, because we are creating a BST. Okay, so if a BST is not there, this method we have to use. If the BST is there, we have to use this method. So as the question was for general logic or the general tree, we have to only use this method. Okay, so this will give us a correct answer. So this is for the general binary tree, and this is for BST. Okay, so the time complexity of this approach is, as we are finding, searching time complexity is nothing but uh, order of n only for this particular approach. Okay, but if the tree is BST and the tree is balanced, then the searching will be order of log n. But as this is just a normal BST, it is not a balanced BST, so this will also be order of log n only. Let me write it. It is order of n as it is not balanced. Clear everyone with this question? So very simple logic. Okay, we are finding the we are recursively finding this thing. So now just assume that the recursion is not there. Then what you have to do? So you have to create a stack. Even that is as the question is simple, then that solution is also simple. So, but you have to create a stack, push all the elements into the stack, again pop all the elements from the stack. Then while you're popping, just compare it with some minimum value. You have to maintain a min index or something like min value and compare it with that, and keep updating that thing. So logic wise, you can implement it iterative and recursive also, but simplicity of writing the code is more in recursive. So if you see, this is only 4 lines of code. If you're writing iterative, you have to write like minimum of 15-20 lines of code. Okay, with this, I think we are over the time, and the next session we will see balanced BST, which is nothing but ABL tree, and we will solve few problem statements as well. So I hope now you have some idea about nonlinear data structures, about the tree, about a BS tree, insertion, deletion, traversal, and all those stuff. So I'm sharing this logic with you all so that you can go through it later. Guys, I've sent the code to you all, and just check whether you have received it or not. And I think it will not to be sent to the persons who are using in mobile. I don't know, means it was the case previously. But if someone is not getting it, then try to share it in your WhatsApp group or something and share with the other persons who have joined the session through mobile. Okay, guys, so let's finish the session for the day. I'll give this as a homework to you, maximum depth of a tree. So I'll explain the question and then I'll leave it to you. So let's say you are given a tree like this. Let's take this one only, 9. So again, this is not a BST, it could be any normal tree. Let's say 1, 3, 4, 3, 4. Okay, you have to find the maximum depth. Maximum depth. A depth is nothing but the number of nodes. Okay, number of nodes between root and leaf. Okay, so there are how many leaves? There is one leaf, there is one leaf, there is one leaf, and there is these are the leaf nodes. Okay, so as we are finding maximum depth, we have to find out maximum number of nodes. So what is the maximum number of nodes? It will be this path. So this is the path. So here 1, 2, 3, 4, and 5. So answer should be 5. So given a binary tree, you have to find out the maximum depth. A depth is nothing but the number of nodes. Again, I am being very specific. Depth questions depend on the problem statement. Depth can be maximum number of edges. Depth can be maximum number of nodes. For this thing, I am giving you maximum number of nodes. So find out the maximum number of nodes present between the root and the leaf node. Okay, so I want the answer to be 5 because there are 5 nodes here. Where is it? 1, 2, 3, 4, 5. So this is the homework. You just try to find out. Leaving the question in the chat. This is the one. Find the maximum depth of a binary tree. Depth is nothing but number of nodes between root and the leaf. Okay, so yeah, that's it, guys. So let's finish the session and meet on the next fundamental idea, guys, of creating a logic for trees. Just take this particular combination. Okay, so all you have to do is when I am at this node, what should I expect from my child, and what should I give it from a parent? Okay, that's the only thing. So expect from child. Expect from child. That means from recursion. and what should be the output? What should be the output? Output of the node. Okay, so when I'm at this particular node, so what is that thing that I should expect from my child? So what will these two recursive functions give me? And based on those two outputs, so whatever these two are giving me, what should be the logic I perform, and what should I return to my parent? So what should this 4 return to the parent? So if you can just think of these two steps, then the solution will be very easy. Okay, you can formulate a solution very easily. There is one more step that you can involve here is, okay, whenever you are expecting, what should be the input given to these two methods? So sometimes we have to also pass input to the child. So you keep that also in mind. So what are you expecting from the child? Okay, before expecting, what is that you are giving to the child? What are you giving to the child? What are you expecting from the child? What is the operation that you are doing within yourself, and what is the output that you are giving to your parent? Okay, again, when I say your parent, your child, it is all related to this thing, this tree node. Okay, so I hope you all followed today's session. Let's meet in the next session and then discuss few more problem statements. So I hope you are good for the day. We can stop the session now. Okay, I think we are good. Okay, thank you all. Let's meet in the next session. Till then, keep practicing. Remember, practice recursion as much as you can. Okay, thank you all. Let's meet in the next session. Bye.